So we have already introduced scalar line integrals, and we would like to begin with a reminder. So imagine that we have a domain in 2D or 3D, and we have a curve C on that domain, and f is a function defined on that domain. Technically, f is only required to be defined on C, but usually that's the case for this. So the question is, what is the scalar line integral of f along C? And at least for computational purposes, what we need is a parameterization of the interval AP by a vector valued function R. And then this integral will become the integral of f of r of t times the speed of the corresponding motion from A to B. And just to give a simple example, let's do a three-dimensional example. So compute the integral of xy ds along C, where C is the helix parameterized by. So here we will give directly the parameterization. So this will be cosine t, sine t, comma t for t between 0 and pi. Okay, so this is what we would like. Let's make this pi over 2. This is what we would like to compute. And obviously, there would have been a geometric way to actually describe this helix, but this way all we need to do is just apply this formula. And in order to apply this formula, what we need is to find the speed and find also the pullback of the function f onto the interval of the parameterization. So let's begin with the speed. So we have that r prime of t is negative sine t cosine t comma 1, and the magnitude of this is square root of sine square of t plus cosine square of t plus 1, and of course this is equal to 1, so that becomes square root of 2. And then we have f of r of t is going to be equal to f of cosine t comma sine t comma t, which means wherever you see an x, you have to put cosine t. Wherever you see a y, you have to put sine t, and wherever you see a z, you have to replace it by t. Here we only have x and y, so this would give us cosine t times sine t. And when we put everything together, we will have the integral from 0 to pi over 2. That's the interval of parameterization. Cosine t sine t times square root of 2 dt. And here we will do a change of variable substitution. So u is equal to sine t. Du is equal to cosine t dt. And this will give us the integral from 0 to 1 u times square root of 2 du. We put 0 and 1 because we apply the substitution to the endpoints of the parameterization, and this would give us u squared over 2 times square root of 2 from 0 to 1, and that is going to be simply square root of 2, right? So actually, it's 1 over square root of 2, so 1 over square root of 2. Okay, and that's it. So now we would like to make the transition to vector line integrals. And in this case, what we do is we have a domain. Again, we have a path C, but this time around, we would like to specify where it begins, where it ends, and what the orientation of traversing this path is. And then in the domain, we suppose that we have a vector field, F. So what we wish to compute, or what we wish to define, is the integral of F dot dr along C, where C is oriented with the chosen orientation or direction. Now, this integral has a very simple physical interpretation. So if you have a force field, then this integral will represent the work that is produced depending on the sign. It will have to be something that can be harnessed or something that has to be spent in order to execute the motion. But the work along this motion in this direction along the path. So one could have actually defined this by starting with a scalar line integral and pretty much take the projection of the force along the path of the motion. But it's equally simple to actually give the formula by starting with a parameterization. In all these cases, we do need to begin with the parameterization. So what this is going to be is the integral from A to B. A and B are the endpoints of the interval of parameterization. And we will have simply the pullback of the vector field on the domain of the parameterization, dot with the velocity, and that is what we need to integrate. So just to make sure that we understand the structure of this particular integral, this is a vector, right? This is another vector. And when we take the dot product, the whole thing becomes a scalar. And we just integrate this function that we find. Okay, so let's begin with a simple example just to see how this goes. Before actually I do the example, I would like to mention some alternative notation that we have here. So if the vector field is as components P and Q, so these are functions of X and Y, then we can also denote the vector line integral along C as P dx plus Q dy. This is a very unusual notation that we have in this case. And obviously, if you have a 3D vector field, you will have one more component. Okay. And there's one more detail that we should mention here. If the path that we have is closed, it's what one can usually refer to as a loop. Then, instead of writing just FDR, we can emphasize the fact that the path is closed by putting a circle on the integral. And of course, this can be added in the case that we have the other notation in the spirit of Leibniz. Okay. So this little circle will indicate closed path. So a closed path is a path that starts and ends at the same point. So with all that, again, our main focus today will be to start with a parameterization of the path that we're given. Now we have to be twice as careful because we have to make sure that the orientation is compatible with the parameterization that we choose. Actually, if it's not compatible, it's not really the end of the world. What you will find is the opposite number for the vector line integral. So in fact, one might argue even the following way. You might say, well, if you have a parameterization and you realize that it's in the opposite direction and you don't want to find the, to reverse it, then all you need to do is just compute the integral and then multiply it by -1. However, I should emphasize here that reversing a parameterization is the easiest thing in the world. Let me just show you how this can be done. So if you have a path that you want to traverse it, that is traversed, let's say this way, and is given by a parameterization R of t on AB, if all of a sudden now you want to traverse it the opposite way, then what you can define is another parameterization R1 of t, which is equal to R of A plus B minus t. And again, it will be defined on AB. And this parameterization really traverses the path the opposite way. You can see it. If you set t equal to A, then you find B. If you set t equal to B, you find A, and then you get everything in between in the opposite direction. Okay, enough with all these preliminaries. Let's dig into an example now. So as an example, let's compute, let's use a little the Leibniz notation. Let's have a little fun here. So let's compute x dx plus y squared dy along C, where C is the part of the parabola y is equal to x squared traversed from 0, 0 to 1, 1. Let's see how this works. So first of all, let's sketch this path. something like this. So y is equal to x squared, and we go from 0, 0 to 1, 1. It seems that the proportions that I chose here leave a lot to be desired, but regardless, let's work with this. The orientation of this path is like this. And one of the things that we're going to need is a parameterization for this path. This path is part of a graph. Every graph can be parameterized by t, comma, f of t, where f happens to be the formula, the function, the underlying function that gives rise to that graph. So we can take r of t here to be t comma t squared. X squared is the underlying function, and t goes over the interval over which this graph is defined, so from 0 to 1. So here's your parameterization. Okay. Now, we need to identify the underlying vector field. And what is the underlying vector field? According to the notation that we introduced, it's x comma y squared. And we will need to find f of r of t. So we pull back the vector field onto the domain of the parameterization, which literally means that wherever we see an x, we replace it by t. Wherever we see a y, we replace it by t squared. And that will give us t comma t to the fourth. We now want to find the speed, the velocity. That's very different. So 1 comma 2t. And finally, the last part that is needed here is to take the dot product between the pullback of the vector field onto the domain of the parameterization and the velocity. Let me actually write it as r prime of t. And this will be t comma t to the fourth dot with 1 comma 2t, which is t plus 2t to the fifth power. And that's what we need to integrate from 0 to 1. And that's all. So as you can see, you have a whole bunch of interpretations to make, and eventually you find a function that you need to integrate over the domain of the parameterization. And this will usually be very simple. So t squared over 2 plus 2 6 t to the 6 going from 0 to 1. This would give us 1/2 plus 2 6, also known as 1/3. And this would be 5 over 6 if we clear denominators. And yeah, that's our first example. Okay, let's do a different one. Let's make it a little more interesting, and let's do actually an example that will play an important role in one of the things that we will do next time. So let's look at the following example. Compute the this time it will be over a closed path, and it will be minus y over x squared plus y squared dx plus x over x squared plus y squared dy, where c is the unit circle. I can't just leave it at that. I need to give you a direction, traversed in the counterclockwise way. So we've seen how to parameterize a circle. I would advise you to try to pause the video and try to see if you can come up with the setup for the integral yourselves. And of course, now let's do it together so that you can check your work. So again, let's sketch the circle. And we're going the counterclockwise way. And of course, we know that this is parameterized by cosine t, comma sine t for t between 0 and 2 pi, because we want the full circle now. Nobody said anything about part of it. And of course, the integral has the closed path sign, which means that, again, it's all of it. Okay, so what is the underlying vector field? Let's identify the underlying vector field, which is minus y over x squared plus y squared. Let's put I. Okay, we haven't used this notation too much. And x over x squared plus y squared j. And what is its pullback to the domain of the parameterization? Well, we have to replace x by cosine t and y by sine t. And then notice something really cool that is going to happen here. The denominator will end up being what? Cosine square of t plus sine square of t, which is equal to 1. So the denominator is gone here, right? And what you will get is simply minus sine of t times I plus cosine t times j. And the velocity is going to be minus sine t comma cosine t. If you want me to use the same notation with I and j, then it's going to be precisely the same thing, which means what? That when you eventually take the dot product between the pullback of the vector field onto the domain of the parameterization and the velocity, what do you get? You get sine square of t plus cosine square of t. So we multiply actually this with that and this with that, and then we add them up, right? And that's simply equal to 1. So after all this effort, what we need to integrate is simply the function 1. And of course, we do that from 0 to 2 pi. And what we get is 2 pi. And that's all. Okay, I think we should do one more example. So we did a circle, we did a graph. Let's do a line segment in 3 dimensions. That should be a good conclusion for our examples. So example, let's try now the first notation that we introduced. So compute f dr along C, where f of x, y, z is equal to x to z minus y squared, and C is the line segment from the point 0, 0, 0 to the point 1, 3, negative 2. Okay, a rather generic example, nothing too special about it, but let's see how we execute everything that we showed so far. And again, I would suggest that you pause the video and you try to set everything up. So this time around, I'm not going to try to tell you exactly where this point is. So you can see that It has to be somewhere in the lower z space, but the path is going to look like this. And supposedly this is the 0.13 -2, and the parameterization will be what? It will be 1 minus t times the first 0.000 in vector form plus t times 1, 3, -2. So again, the point vectorized, and this will be for t equals between 0 and 1. And certainly we can slightly simplify this and write it as t, 3t, -2t. What is the underlying vector field? We have already given it. I'm just rewriting what is written on the top there. So it's x to z minus y squared, and f of r of t is f of t, 3t, -2t. And now I'm going to replace x by t, so that will give me t here. Z by -2t, so that will give me -4t, and minus y by 3t, so that will give me -9t squared. And now I'm going to take the dot product with the velocity. I need to find the velocity first. This is a constant vector, so it's 1, 3, -2. How do I get this? By just taking the derivatives of the components with respect to t. And finally, I'm going to take the dot product, and this is going to be t minus 4t minus 9t squared dot 1, 3, -2, which will give me t minus 12t plus 18t squared. And what I need to do is eventually integrate this from 0 to 1. And this will give, so it's minus 11t, so the antiderivative will be minus 11 over 2t squared, and we will also have plus 6t cubed from 0 to 1. This will give us minus 11 halves plus 6. 6 is 12 over 2 minus 11 over 2. That will be simply 1/2. And that's it. So again, this example clearly shows you that computing such an integral is a whole bunch of interpretations. So you need to find f of r of t, you need to find r prime of t, you need to take their dot product, and eventually you integrate this over the domain of the parameterization. And that's all for today. Thanks for watching.